Hello everyone, welcome to another problem session. So this is a standard problem and concerning Betatron. Maybe you know particle accelerators. It's like one of the fundamental instruments in particle physics, experimental particle physics. So it's quite a complicated instrument, and it took many years to develop it. But the idea behind that is quite interesting. Okay, so you want an electron. You want an electron to be go in a circle of fixed radius r, and you don't want it to accelerate it using fixed electric field. So one way to accelerate, that you can have a positive plate here, negative plate here, and if you release an electron here, it's going to accelerate towards that. It's kind of linear acceleration, and basically electric field is that way, electron is going to go opposite to that, accelerate. So here you're going to go in a circular orbit. However, so this is an electron, and it's going to go in a circular orbit this way, but I want to speed up as it goes more and more orbits. I want to have higher and higher energy, and you can get very close to the speed of light. So how do we do that? So if you have a magnetic field, you probably know this. If I have some magnetic field, if a magnetic field going in the board, so if you shoot an electron, then if you use the right hand rule, if the electron is coming this way, let's see, if the electron is coming this way at some point, then if the velocity is this way and this is the b, then you do right hand rule. So you go left, so go down, that means force will be up, so force will be up. And if you follow this electron, of course it's going to come here and get out like that. Or if you have magnetic field sufficiently, then it's going to be a circle like that. So it's going to go in this circle. And if this is B is fixed, then no magnetic flux change occurs, and so it can't be accelerated. So the trick is that you have a field which can maintain the circular orbit, but then you want to speed up. That means you through this area, you delta phi, you change delta phi is not zero. If delta phi is not zero in some delta t, then you should have, then in this orbit there will be EMF induced, and it will give then EMF induced in the orbit of the electron, in orbit of the electron, and then that means electric field, and that means electric force. So unlike this situation where you have, at a Mach, the whole going electric field at every point is pointing that way, well, in this situation, electric field will be, say, over here will be pointed, say, that way, and over here electric field will be pointed that way. Over here electric field will be pointed that way. So it will just keep accelerating it, and if certain conditions are met, which is the point of this question, then when it comes back over here, electrons comes back over here, is going to have higher energy, which means I need to correspondingly adjust this magnetic field so that we need the orbit remains the same. So this is the condition that we need to find. Okay, so that's the question. So if you know how to prove this relationship, go ahead and try and attempt at it. It's not that hard. And you can pause this video and come back and see my solution. Okay, so because we're going to do this problem in XY plane, and this is a circular orbit, it's a good way to do is just let's see origin here, and let's call this x-axis, and let's call this y-axis, and the z-axis is coming out. So z-axis is along which we have B pointed. Okay, so the B, whether any point over here or pointed like this, so those are the B coming out. So the B is coming out, so B vector will be simply at some x, y, z will be some B x, y, z, but in terms of k hat. So it's going to be like that. Okay, so that we can be very direct about the whole thing, and we will not even depend on z, just in the xy plane. Okay, so you can say there's a couple of relations you can immediately obtain. One is it's going in a circular orbit. So let's this and I know it's going to increase with the speed, but at each instant, if I look at it, if it has a speed v here, then, and the magnetic field at that point is B0, BO, that's the magnetic field at the orbit, this is the orbit, and it's coming out. So you use right hand rule again. So if you do right hand rule, it pointed out, then it's going to point in. So you can see the magnetic force is the one that's going to point in, and that's going to be centripetal force. So that's so Fm is just going to be we have a minus E for the charge. So we could have written this as a Q, just to save time. B and the perpendicular, this is an XY plane, this is Z direction, so this is going to be QVB, that's sine theta equals to 1. And this is same as there's going to be mass times centripetal acceleration, which will be pointed, so this is radially pointed, so this is radial, and so this acceleration will be radial, and this is going to be m minus v square over the radius is capital R. So you can see that mv equals to charge, let's call this Q. One of the V is cancelled out, Q QBR, and this is all doing non-relativistic. So we are trying to already making an assumption that speed is not very high. We can be the non-relativistic formulas we can just use. So of course, when you get to the relativistic, you have to do all of this thing all over again, right? So this is the momentum at this instant. Okay, so let's call this one equation. Okay, now let's look at a flux through this what's the flux through this area will be? Well, flux through that area will be at this instant, flux will be equal to B, which B this point, say any point, say P. So B at any point inside there, P at some point P dot n hat dA, and this thing is a little element of this at point P, right? So this is all point P and over this area. So this is the surface S. So this is the magnetic, so S is not changing, but BP has, if you work this out, this is, if I divide by the area, I will get an average. So anyway, this should be, if I knew the average, then it will be some kind of, if there was an average over this, which is what this is. So B average is, so this is kind of B average by R square. Okay, so we can actually do this. Another thing we can say, so this is how you're going to get the phi. So we can say we have a good handle on that. Let's call this equation 2. Not very useful right now. I would say, how is it accelerating? Well, there must be electric field along this thing. Well, that has to do with delta phi. So you will say EMF going to be induced here, which will be E dot dl over this circuit. I go around there in that direction on that circuit C, on circuit C, and that should be minus d dt of phi. Well, when you look at this from the symmetry, we have a symmetry of a cylindrical symmetry. That means E will have same value everywhere, and it's always going to be along the orbit. So this dl is along the orbit, and this is along the orbit. So this should be whatever it is on that orbit. We're going to add the orbit times 2 pi r. So electric field at the orbit has this value. Well, let's call this equation 3. So we have relation of phi. We can do integration. This is constant, this is constant, this is, so that's the rate at which B average is changing. Okay, so let's see, now we can relate this EMF to get the electric field. So the electric field is basically just equal to E0 equals to minus 1 over 2 pi r delta phi delta t. We're just going to write like that for now. Now, if you know the electric field at the orbit, then we know how it's accelerating, and that will relate to the change in momentum. So let's call this 4. And then over here, let's see what the force will be. So force can be equal to delta P delta T, and this force vector is all radial, I mean angular. So this force is let's see, if you do this was radial, right? This force was radial, but change in momentum vector, change in delta P vector. So momentum is pointed this way over here, and then this way over here. So change in the momentum vector with time should be, as far as this guy is concerned, there are two different types of forces here, right? This force is this force over here is balancing, keeping in circle, and this force, the force associated with this, is actually going in the circle. So this force is along the theta direction. This direction is theta direction. Force is along the theta direction, right? Angular direction. So that is equal to, I got a minus E times electric field, and this is along the theta direction. So that just equal to that. And what's the force? Well, if this is the momentum, then force will be change in momentum over change in time, you know. And so this would be, if I put this over there, I get E over 2 pi r delta phi over delta t. And these are all, this is a momentum is in the angular direction, and the force is angular direction. This momentum itself is, if you look at momentum vector is has a some pz coming out, k hat direction. This is 0. There's no radial direction, so p radial hat, this is 0. P theta angular direction, theta hat. So this is the only one that we're looking at, and this is what we're calling p theta hat. And so that's using a little bit reduced notation, like more simpler notation, right? I hope this is clear. So we can actually you know, cancel out this and integrate from 0 to some p and 0 to phi, integrate formally. So we get p equals to E over 2 pi r phi at some time t, And so we wrote out some formulas over here. P of t is P of t, if you look over here, is this was B at O. So this is B at O because I'm looking at that orbit, B at O. So P is that. So the left side, so this equation number 5, and this one using 1, and on the right side using this guy. So we are going to get what answer we are going to get this, because we got PT is going to be some charge B0, this is actually capital R on the left side, and on the other side is some charge over 2 pi r, and this is B average times pi r square. So you can see things are going to nicely cancel. This r with this r with this r, all the r's together cancelled. This pi cancelled. So B at the orbit, B at these points, at these points, B at the edge on the orbit is actually half the B, the B that is average over this area, and that's an important condition. This was derived very early on, maybe 19th century, early 20th century. It was derived and was not quite implemented. There were some technical issues to implement this. It took a long time to get the Betatron, functional Betatron, and to work. Okay, so this is an important problem actually. There you can see the whole bunch of different parts of physics come together in this problem. So if you're not able to do this right off the bat, it's okay. Maybe you can do it now. Maybe you can write it out in more coherent language a couple of times and satisfy yourself with this condition. Okay, that's it. See you. Bye.